Hello, everybody, and welcome to meeting 4 of the Remove the Bytes working group, our bi-weekly numerous meetings spread across a couple of months working group dedicated to building better data transfer protocols. We've got a packed schedule today, so lots to get through. I'm going to try and quickly shuffle through a quick agenda. First, around some revised purpose, based on gathering some feedback and notes from other folks. I'm going to take ideally less than 10 minutes to talk through some of that. Then Guillaume is going to talk to us a little bit about his findings from doing research on bit swap measurements, which I believe are now finalized, and I have had a chance to read through, and they're super exciting. And then we have Adine, who's going to be talking broadly about the intersection of what a data transfer protocol starts and stops when we're talking about incremental verification and other things. I'm excited to hear Adine's talk. We haven't had a chance to coordinate yet. And then we'll have open discussion. So moving right along. Couple of lessons I've gathered from a number of folks. I've sought feedback from a bunch of you over the sort of before the break started. And I want to sort of just revisit what our original purpose for this group was, which was to ship a data transfer protocol that can replace bit swap in Q1 2023. The IPFS account tweeted this, and I actually had people reaching out to me saying like, wow, that's pretty ambitious. And like the timing on that's really well. I'm like, yes, we've gathered feedback on that and we're refining the purpose of that. But to give you a sense, our original timeline, which we are still kind of following, we're on meeting 4. Hannah is scheduled to speak at our next meeting. On the original timeline, we were going to select a protocol, implement it, and recap it, and sort of present everything by the end of that on the 29th. That I think we should revisit that. And I think we should revisit what the group's purpose is and make sure that it's actually in line with what I've been talking with folks about what is useful about this working group and how we can sort of still accomplish a lot of these high level goals, but maybe not with as much like, hey, we're all going to agree and do this and sort of move and coordinate really in this sort of tight and direct way. So a couple of things that I've also want to share a couple of things that we've learned steering this group as the number 0 team. Specifically, we've learned that the actual shared infrastructure of this project has been far too expensive to maintain. We've had a couple of challenges getting folks to contribute outside test plans for the test ground structure we set up, despite writing sort of a README on how to do that and getting everything set up in place to sort of accept new plans. And then the actual maintaining of test ground itself has been a really big and hard for us. The other thing that it really competes with is something that Juan talked about in our last meeting. For us as a team, we're really fired up about this experimental loop. And I think that one thing I want to call out is a distinction between the test ground infrastructure we have been maintaining for this group and an experimental loop. And the distinction being, if you look at all of these really fantastic screen grabs, this is all stuff that is tightly tied to a single project and running usually in CI, where you actually have continuous feedback for engineers as they're working on their own protocols. And if we contrast that with what we've been doing with the test ground plans in this working group, that has really been focused at infrastructure that spans across projects, right? I think that if we look at our core value proposition of what some of these initial metrics reports produce was something like this, that gave you this really sort of like high level, pretty ambiguous, but at least like somewhat meaningful apples to apples comparison of a bunch of different data transfer protocols. And I think there's a way to accomplish a lot of this without building that shared infrastructure. And I think the fundamental lesson that I'm taking away from last year was that this experimental loop should take precedent for all of the teams, and that building this really nice set of instrumentation and feedback into your own project is probably a better use of everybody else's time. And so what I'd like to propose is that we repurpose this group a little bit. And while this might seem like a big sort of step down away from like, let's ship something towards, let's compare notes and be friends. I think it's still actually quite meaningful and useful to lean into the things that have been really working from this working group. We've been getting some really great presentations on findings and research. I'm particularly excited to see the presentations today. I think he has some really insightful pieces to present, and that getting that information out to folks working on data transfer protocols is super useful. Having sort of like trying to get everybody, cajole folks into PRing in their data transfer protocol into some shared, highly expensive to maintain test ground resource is really not working for us as a group. And so I think the purpose of this group is actually not about shared infrastructure, but instead about making the stuff we make comparable, right? If you look at, I think a great example for this is the world of hash function comparisons, where you can pretty easily benchmark, hey, this is how Blake 3 compares to SHA-2. And like, we have lots of arguments, but at least the way that works in practice is there is a shared set of metrics that everybody uses, and everyone publishes their own benchmarks. And you have a meaningful way to sort of compare different things by looking at that shared nomenclature and that shared set of approach to measurement. And I think that's really this group's purpose. And I'd like to sort of welcome folks' feedback on that. But I think we can honestly keep a lot of the original timeline, but instead of saying, hey, we're going to select a protocol, let's select a shared set of metrics, and let's have our individual projects publish benchmarks that are naturally comparable, because we do publish benchmarks that are apples to apples, where we use the same definition for the same thing. And that will make it such that it'll be really obvious to see what works for what use cases and in what contexts on a recap at the end of this. And I think that's a more useful sort of approach to sort of the way that we should be working moving forward. I'm going to sort of like, it's a lot to talk about here, but I think that's probably the most feasible way forward. And I think that at the end of the day, that does mean we can still produce a protocol that can replace BitSwap, but this group has to like help us define what a good replacement looks like. In particular, reading through Guy, some of your conclusions around scaling of the network and messages per peer and messages per CID. I think we have some like really interesting properties that we need to look at. But I think this group can really do a lot of meaningful and impactful work around that without necessarily needing to develop the overhead that produces this like charts every week and deadlines every week, every 2 weeks. So maybe that's a lot, but that's based on sort of like a lot of individual conversations I've had with a number of you. And I guess we'll take, Hannah, I'll take a question from you, and then maybe we'll move on, try to move a lot of this conversation to the discussion section at the end. But Hannah, take it away.
Yeah, I think that makes all those things sound 100% good and realistic for the Q1, the original timeline. I'm just wondering, why don't we continue the timeline after that with the goal to try to get to the original goal? Like, because the one thing that would be, there is a hard conversation that comes around like, okay, let's all agree and start adopting, and it would be a shame to completely lose that. I think it's absolutely realistic that we are not in a position to like make that decision in 2 weeks. But I like, yeah, I'm just saying, like, I think it would be, I think like all that sounds good. And then like when March comes around, like, I hope we don't disband. Like, I hope we, I hope we continue until we hit our original goal, like, I don't know, for discussion amongst the group, just because I think that that like with all the things that we would have in March, we will have the grounds from which to have a very difficult discussion, which is a necessary discussion, in my opinion. Yeah.
I think that's great. And I want to sort of leave that as food for thought for others. And then let's transition now to Guy, who's going to give us a really nice tee up of some core insights that have now sort of calcified. Sound good?
Yeah, let me share my screen.
Hopefully you can do that. Okay, cool.
All right. Can you see it? Okay, so hi, I'm Guy, working with ProLab on measuring IPFS component mostly. And I will present today the result from our study on BitSwap. And so in particular, I want to point out that BitSwap has two roles. It does the data transfer, so that's the reason we're here. But also it does some content discovery, some content routing. And so that's mostly what I will be discussing here. So I will be discussing the effectiveness of the BitSwap discovery process. If I can change slides. let me stop the sharing and start again. All right, sorry. So the motivation to measure BitSwap was that we wanted to know whether BitSwap was efficient to discover content or not. And it is, so in this regard, it is a bit a concurrent to the DHT because both of them try to find the content. And then anyway, if you get an answer from the DHT or from BitSwap, you're going to fetch the content from BitSwap. And we also, we try to get rid of IPFS magic number, which are the constant number that are shipped in IPFS and are constant, and we didn't really test the value. So here, the way BitSwap works, it's first when the user makes a request, for instance, IPFS get, it will first, so BitSwap will first broadcast a request to all of its connected peers. And if BitSwap didn't hear back from any other peers, from any peer, within 1 second, it's going to make a DHT lookup in order to find where the content is located. And so the motivation is to test whether this value of 1 second is appropriate for BitSwap, or if we should, for instance, decrease it or remove it at once. So we have done some measurements. So basically, we needed a list of CIDs in order to reproduce some requests. And we got those by sniffing the network. So for all of the BitSwap requests, so simply running a BitSwap server and listening to all BitSwap requests. This gave us a list of CIDs. We modified BitSwap in order to give it 15 seconds to find a block instead of 1 second. And it's going to fetch only a single block, which means that if I don't know, I get the root CID, I will not try to resolve any other, so yeah, basically the content inside this block. We also prevented BitSwap to use the DHT, so we wanted to observe only BitSwap and not BitSwap and DHT combined. And in the case that BitSwap failed to discover the content, we want to verify that the content is available in the IPFS network. So we did a DHT walk in order to verify whether the content was accessible. And so we run all this from a VM in Central Europe, which can be relevant for latencies measurements. So the results we had is, surprisingly, we got a very good discovery success rate, which means that, so within 15 seconds, over 98% of the CIDs we requested return positive. So which means that the requests we broadcasted were almost all positive. So at least one of the directly connected peers had the content. And we also learned that it's very heavy. So it means that for every single request, more than 150 peers are solicited, which is a lot. And so there are more than 1,700 messages that are sent, which is roughly 2 for each connected peers, 1 for the request, so the won't have, and 1 for the cancel. Now, trying to explain these results, out of roughly 50,000 requests, we got that most of the content was served by a small number of providers. By looking at this number, for instance, we got that the top 20 peers, so the top 20 providers, are providing 75% of all the blocks that are served. And we double check that the list of CID is representative by taking the logs from the IPFS gateways, and we got similar performances. So we expect that there are a few peers in the network that really serve a lot of content, and most of the peers are saving few or no content, or the content isn't widely accessed. And out of the 10 top providers, we get that 6 of them belong to NFT.storage. And the rest, we don't know. Maybe NFT or Web3.storage, but I couldn't get, couldn't match the peer ID. Now, looking at the latencies, we got that most of the successful BitSwap requests were coming back within 1 second or even smaller. So here we can see the latency for both discovery and fetch, which means that it's in the best case 2 RTT, because first I'm gonna send a want have, the remote peer is gonna reply with a have, then I will send a want block, and the peer will give me the block. So it means that it's the time for 2 RTTs. And if we zoom in, we get that even like almost 80% of the requests are served within 200 milliseconds, which is fast. And that's 2 RTT. So maybe, the figure would be shifted to the right if the location of the test host was in a remote place, like it was in Central Europe, so I guess close to the content. Maybe in North America would be the same, but in New Zealand, I would expect to see a shift from a couple 100 milliseconds to the right. So the main takeaway from this study is that we measured that BitSwap is fast and accurate, which means that we find most of the content during this first second of BitSwap broadcast, and it is very fast because it's coming back in 200 milliseconds in most of the cases. But however, it is inefficient because for 1 block that I want to fetch, I will send I will solicit more than 800 peers, which is really a lot compared to the DHT. The DHT is at most 20 peers, I would say. And but however, the discovery content discovery for BitSwap doesn't scale, because in order to keep the same accuracy, so if we still want to have 90%, 98% success rate when discovering content on BitSwap, when the network goes 10x, then we need to have 10x open connection to be able to keep the same discovery success rate. And so that's why it doesn't scale, because we have a limit on the connection manager. And also something worth noting is that we have a small number of peers that serve a lot of content. So maybe there are some easy optimization to just try to send the broadcast to the top provider instead of flooding the whole network. So that's, so some direction. And concerning the once again, latency delay, I would say that setting it to 0, so removing it at once, would make it better, because the, let's say, network overhead would be only 3 messages, because it's the concurrency parameter of the THT. So going from like, now we have like 1700, and if we add just 3 messages, it isn't a big overhead, and it would make the tail latency 1 second faster. So for in the case BitSwap doesn't hit the content, in this case it will be 1 second faster to resolve. So it's not expensive to pay, but the improvement is not huge. And so all of the references are in this report, so you can follow the QR code, or just read through the report. And so another point is, do we really want, I mean, it's more an open question, but do we really want to keep, so at the moment BitSwap has both data transfer and content routing, or let's say content discovery, bundled together. And I'm not sure whether it's a good idea to keep them together. Sure, it's fast, but I'm not sure at some point if it will still scale, or if we should, let's say, optimize content routing and in a different way also optimize data transfer, both in different, let's say, bundles. instead of having Bitswap doing both at once.
Fantastic. So many questions have appeared in the chat, Guy. And so I'd
Okay.
love to, so instead of asking you answer them out loud, what I'd love to do is let's keep that conversation happening in the chat. We'll capture a lot of that in the notes and bring it up in discussion. I want to keep moving right along if that's cool. This is a super great talk, but I think we should do Adine next, and then we can move to open discussion. Adine, are you ready to roll?
Or some definition of ready to roll. So, all right, figure out how to present. All right. All right, everybody. So this is a little hastily put together, but overall, I had some thoughts on data transfer that maybe are a little different, I think, from what we've generally been talking about. And one of the things that sort of was pushing me along this route was thinking about sort of block limits and things like that. So let's just get to it so I don't eat up all the time here. All right. So all right, start with, we'll just take the sort of Adine opinionated view of data transfer, so you see where I'm coming from when I say crazy things. So a little bit about what we have so far, and talk about large blocks, and then at the end, implementations are not protocols, and that has good and bad pieces associated with it. All right, so data transfer things. IPFS is peer-to-peer tooling. It's tooling for the peer-to-peer web that uses content addressing. So this is not how do I make Akamai do things better with, using hashes for caching. It's not how do I do sub-resource integrity in browsers when I download the thing from Twitter. This is not how I do friend-to-friend networks, which is Git. It's not peer-to-peer distribution of like the one true ultimate file format, which is what BitTorrent does. And then this one, which is like a little spooky and controversial, but came up in Iceland last year, was basically that nope, nobody seems to be interested in defining IPFS itself as if you have exactly A and B and C wire protocols and data decoding modules, then you have IPFS. Some people like that, some people don't, but that seems to be where the impetus is after Iceland. But we can use IPFS tooling outside the primary domain. So like, there's no reason you couldn't use IPFS to do Git things or BitTorrent things or Docker things or CDN things. We're providing abstractions, right? And sort of interestingly about providing abstractions is that it turns out no application writes on an abstraction. It doesn't do exactly the abstract thing. It does what that application needs it to do. And so people will sometimes punch through the abstractions when they want something a little more, right? If you decided you were going to build basically BitTorrent on top of IPFS, you'd do it. And then you'd say, hey, you know what? I might be able to eke out some data transfer speed if I make a data transfer protocol that's specific for what my data structure looks like. And then decide, is it worth it? Is it worth a specific data transfer protocol for me? Or is like what I have good enough? Right? This is going to happen sort of everywhere. So as Brendan sort of mentioned, I think making the best protocol ever, probably not the thing. Whether it's things like we want to reuse data that we've hosted that's already hosted with other protocols, like how web seeds work with torrents, where there's an HTTP endpoint that has a file and you want to use that to host the bytes, and somebody else hosts the metadata that lets you verify it, but like someone else is hosting the bytes. So this means HTTP get resource and get out bytes is like a protocol we probably want. Maybe you want one that's optimized for your application or data structure. Git has a very particular application in mind in how it handles both mutability and trust, right? That makes it optimized for what they're doing. And then there are just high-level trade-offs where people are going to want slightly different things. So maybe we want a few reusable protocols that are like not that hard to implement that get the job done. And I think important, and I only do a little bit of this here because only so much time in the last 4 hours. But having a framework to understand the trade-offs and opinions that come into this, so that when we come down to like, how do we want to build new protocols, as mentioned at the beginning of this session, we like know what we're working with. So backing up a little bit, the user has a request. They give you, there's a thing that they want, right? It could be an IPFS path, that's UnixFS things. It could be some other IPLD thing. It could be, you know, a .torrent file with a manifest of blocks. Content routing is the thing that helps you figure out how to go from some piece of your knowledge of the request to get the data, and then data transfer actually helps you fulfill it. And there's both like a query component and a moving bytes component that's going on here. Because like when I look at, you know, /IPFS UnixFS file, you know, UnixFS directory file, some interesting things there. Most people, when they punch that into like IPFS.io, they don't know whether this is a file or a directory. That's not even specified. Like they don't even know what it is until they get it, right? They don't know if there's a hamped in the middle. They don't really know what's going on here. They have like a more abstract version of this. And what's interesting is that IPFS has sort of, the fact that we've sort of thrown away a lot of information from say like a .torrent file and compressed it to like the root CID or a path, has made it easier for users to work with. And like they generally are pretty happy with that. But it comes with the trade-off that like you are down information in comparison from what you could use to make this thing move faster if you wanted to. And so you have like a query and a move the bytes component, and they're like, they sort of live next to each other. The client for a peer-to-peer environment always needs to execute the query anyway to make sure you got the right stuff. But in you know, in other scenarios where the client doesn't have much information, they might want the server to know what's going on, so the server can help them out in executing the query as well, right? And this is where like, you know, so we have this information gap, right? In addition to the obvious like information of the bytes you're missing, there's a whole bunch of things that if you knew them, your life would be better. Who has the data? Now I don't need to go to the content routing system. What data do I actually need for, as opposed to data I already have, deduplication? What does it look like? So I know which pieces I want first. Maybe I know it's a file. I know it's a video file. I want to download the first couple, I want to download the first 10 megs quickly in a linear way. And then I want to just download everything else in parallel whenever it shows up, because by the time the buffering catches up, it'll be fine. How long is it going to take to deal with each of the peers in the multi-peer environment? Who should I ask for stuff so that I both get it quickly, but without duplicate data? Right, these are all things like we wish we had, and we're sort of operating in a low information environment and trying to make trade-offs around all of this. So some things we have so far. So these are kind of like some big ones, just because we talk about these a bunch, and I just wanted to like hammer them out a little bit. Block-based requests and graph-based requests. So blocks, they're nice. The server doesn't need to know anything. You can implement it. It takes like 0 minutes. They need to know nothing about IPLD. In theory, they don't even need to know multi-hash, but probably they should. And if the requester happens to know whatever they need to know about the data, then everything's great. If you run a .torrent, you have like a .torrent file that has all the blocks in it, like you're good to go. But you don't, when the requester has information, but and they sort of wish they could convey that to the person on the other side, so that the other side knows how to prefetch data, or like send them back multiple things at once, so they don't have to only run the query on the local side, right? That's when like Bitswap is like, oh, please just like kill me. I don't want to download a blockchain 1 block by 1 block for all of eternity. If the blockchain has a finality of like half a second and the latency to some peer that has the data is 1 second, I'm never going to catch up. Like this is just sad, right? Some examples are Bitswap, or like the IPFS, format equals block, thing on the gateway. Subgraph descriptors. there's more information. More information is good. We already went through that. It should just be an optimization on top of block-based protocols because you just have more information. Slightly awkward is that it is an optimization over, say, like IPFS block, format equals block. But a thing that like Bitswap does, which I don't think any of the other subgraph descriptor protocols that we've described do, although maybe, but they easily could, is bundling of requests, which has it's basically a granularity thing, like cache granularity and overhead. And so if you wanted to, say, use GraphSync to make single block requests and just basically treat it as an optimization on top of Bitswap, at least 1.1, if it doesn't have want have requests, you in theory could do that, except you can't because now you have all this overhead because you have no bundling. So it's like that's a totally separate topic from subgraph and block, is just like granularity of request and caching and all of that. Downside is servers need to be smarter. They need to understand however it is you're describing your subgraph. Is it a path? Is it a selector? Is it something in between? Is it whatever? And of course, everyone hates every subgraph descriptor format that's been proposed, which leads to lots of like, oh, well, it should have been this way. Because you're trying to describe like, how do I convey enough information that isn't all the information? Right? There's like something in there that's like just trying to get like the best like bang for your buck here. Right? This is GraphSync, getting car files, crack and sync, car mirror, etc. We have other things. How smart and dumb should the servers be? Bitswap's very dumb. Most other things are smarter. How much work should the servers do? You could compare, say, like crack and sync with something where you just ask for a manifest of all the blocks in the query, and then run Bitswap. And the difference would be that crack and sync would require less upload bandwidth from the downloader in exchange for more execution time and disk loading time on everyone who's being requested from, right? So you're sort of shifting work from the client to the server. And there are reasons why that may or may not be a good thing or bad thing, depending on your scenario, right? You're like deciding who's doing more of the work. Whether this thing should be stateless or it can have sessions where there's back and forth, right? Sometimes sessions are very helpful in terms of being able to like work through, accumulate information over time. And some people are like, oh, I want my stateless thing. Please don't make me have any sessions inside of my service work, inside of my Cloudflare worker. Like, don't do it to me, please, right? Whether these things should be like composable protocols, you use one and then another, or they're like, no, this one protocol solves all the problems for you, right? Composable example would be like, I fetch a manifest and I fetch blocks. An encompassing one would be like, I hand you a graph descriptor and you hand me the whole graph. Should it be extensible or fully specified? I've seen this come up a bunch in libp2p, but it happens here too, which is like, where do things plug in? Should they be allowed to be plugged in? I think generally speaking, people are on board with having pluggability for things like authentication or support for different hash functions or IPLD codecs and ADLs and whatnot. But it's one of those things that you've got to like watch out for and make sure that when you're sending back errors, the errors are like workable with. Or if you're trying to do content negotiation, because in this like the content routing, there's like this dead zone in between 2 and 3 that nobody likes to talk about, because that way we can like give content routing to like, hey, whoever works on DHT or indexers, you go figure that out. And then data transfer can be like, oh, whoever works on like data transfer protocols, you do that. But there's this thing in the middle, which is I got back a list of 100 peers that have stuff. Who do I ask? which is like, it's like the missing piece in the middle there. And you have to worry about that if you're like, oh, I thought you had my stuff, but you don't have all the codecs I need because I just came up with a new one yesterday. And then the granularity, which I just mentioned. Okay, so this brings me to say peer-to-peer transfer of large blocks. Okay. I am going to assume that many of you have seen my prior talk about this and how to do this like safely, but I'm happy to answer questions about it. Short version, we have block limits. IPFS does peer-to-peer transfer, and as a result, it needs spam protection. If it only did friend-to-friend transfer, right, you wouldn't need that. These attacks do happen. There's some links there. It happened to the BitTorrent network. They had some hacks to get around it because the attackers weren't very sophisticated. In V2, what they did is they made the block size effective, like our version of the block size, effectively 16K, decreasing it from like 1 meg or up to 16 megs, right? So they actually went for a much smaller limit than anything we would do or have, and their transfer's working just fine. Because there's a bunch of different pieces that go into this. Whatever magic number you choose here isn't going to work for everyone, right? Some people are going to be like 2 megabytes. My 1 byte per hour upload speed to my satellite in the Andromeda system is like, doesn't want to do 2 megs. That's way too much. And some people are going to say my data center has 100 exabytes per second of bandwidth. 2 megabytes is way too small. But you do this for the purpose of effectively getting along and making sure your data can move to another system and it's okay. But it means that you're interoperable with anyone who chose a bigger number. So BitTorrent v1, Docker, Go, NPM, Arweave, whatever. But we can create incrementally verifiable mappings between, say, a SHA-2 of 100 megabyte block and a graph of, say, 101 megabyte blocks. And we can get this like incrementally verifiably. I'll sort of fly through this, but basically this is Merkle-Damgard. You get blocks, you shove them through the hash function thing over and over and over again, you finalize, you get the output. So we decide we're going to go backwards. We go from the end and we say, oh, well, if I had all the state up until here in the IV in the last block, I could compute the final hash. But then how do I get that IV? Well, I go to the block before and I do that and I go back and so on and so forth to the beginning. So surely, this means that you're just going to roll out a big block protocol that you say, give me large block, and then it gets me the block. But this is just doing what everybody else is doing. All of you who are working on data transfer, whether it's blocks or graphs or both, you're already doing all the interesting work here. So why would I do this? When instead I could reuse the existing protocols so that I don't have to wait for everybody in the world to update before I feel safe hosting the bytes. I can just have my clients update, right? Effectively leverage the dumb servers thing. But how will I bridge that gap? So we're gonna leverage extensible content routing over here. Content routing gives you hints for how to get the data. So instead of just saying peers, who are the peers that give me the data? Instead say, who are the peers and like what is perhaps the CID of a manifest that will allow me to incrementally verifiably get the data. Just sort of shove that in there. It's about the same size as a peer ID. So like, why not? And then we can store that manifest graph blocks next to the real data. Say when I go to my storage provider of, Web3 storage, a Filecoin SP, Infura, whatever. And now I can get I don't have to host any data in order for this to work. I can still use all the existing data hosters, all the existing data transfer protocols, and my client will just make all of this work. And you could say the same for any, we'll call it a common graph request, files in UXFS, BitTorrent, anything that's not anything where you tend to not rely on the fact that IPLD queries mean that you can look at the data from a different perspective. When you're like, everyone really only looks at this with one perspective, you could kind of just put a manifest in there, and that would help you get the job done. So implementations, they're not protocols. We can upgrade the protocols by adding hints in the content routing layer. So does BitSwap now let you transfer 100 megabyte SHA-2 blocks? I would say the answer is still no, still has a 2 megabyte limit, but you can orchestrate something on top of it that does, and that thing isn't another data transfer protocol. That thing is just data that helps you. And so in some ways, like to some extent, like data, you can just have data be the protocol, right? Which is what's helping here, putting manifest in the manifest in the content routing layer, right? Like data is the way you're extending the protocol from the implementation side. It could be a side protocol, right? Like maybe I want to query a large manifest of the manifest of the large blocks from the peer directly, instead of relying on this content routing kludge, because injecting it into the global content routing layer is not great. Like it's good. It's good for getting the job done when you need it to, but it's not going to work when, say, you don't have access to the global content routing layer because you're offline, right? And so on your LAN or whatever, you still need that little protocol extension, like the manifest thing, to get this done. But one step at a time, right? So first you roll out the thing that works for basically everyone, and then you roll out your protocol that allows you to like get this done. Yeah, I don't know if this updated, that slide updated, but whatever. It's fine. Yeah, implementations are not protocols. So like go BitSwap is not BitSwap. Go GraphSync is not GraphSync. This is come on. Sorry about that. Oh, okay. And I guess just a brief note for people who are designing protocols and thinking about large blocks. If you have a block-based protocol, probably I'd just say like you could just return block too big and tell someone to figure it out and contact you with one of the other protocols to get the data. If you're doing a subgraph protocol and then you run across a big block, we'd have to think about it, but I probably what we could do is you could bake into the protocols and say, here is, just as we have extensibility for other parts of the graph traversal, this is how we deal with large blocks. And there are proposals for, this is sort of what like Blake 3 and Bao does. And there's another one for some like HTTP style requests where you basically can send alongside the blocks the pieces you need to verify them as you go. And so, you send block, block, block. Oh no, this one's too big. Okay, let me slice it up into pieces that let you verify them along the way. And that's, yeah, again, not super hard to do because all of this is sort of already done. I think I lost some slides there, but in the meanwhile, I'll just show you this briefly. And I can link to a fancier demo that shows me actually downloading Docker containers, like Docker pull over IPFS. But this is me downloading a SHA-256 of 100 megabyte block from web3.storage, right? And that graph, by the way, just to back onto the implementations are not protocols thing. So this took like 7 seconds. Okay. The graph is linear. You have to go back verifiably one block at a time. So I did not do 100 round trips with web3.storage in 7 seconds. That's not what occurred. Instead, I have a manifest where you're sort of, I have a downloader that's growing trust and incrementally like it's growing trust exponentially. So you send me 2 blocks of good data. I say, okay, well, this manifest seems good. It gave me 2 blocks of good data. Let me ask for then 2 more that are untrusted. okay, it gave me 4 good blocks. I can now do 4 that are untrusted, and I can geometrically grow my trust. And if I wanted that number to be capped or make it lower, I can, but that ends up being a decision on my client, right? My client gets to decide how it wants to do that trade-off between trust and verifiability and protection. Right, the base protocol doesn't have to do anything, doesn't have to be very smart, but the implementation allows me to be smart. I suspect Hugo is going to want to talk about this in a couple of weeks because he has thoughts on how to sort of compose, things like, like GraphSync and BitSwap and other sorts of protocols. Yeah, but implementations they are not the same thing as protocols. I will drop some links in the chat for like people who want to introspect more into what's going on or look at the code. But yeah, that is basic idea. And hopefully it didn't take too long. I think that was 25 minutes. It's a little over.
Oh, good. Thank you, Adine. Open the floor. Who's got questions? Guy, Adine, Gus, what's up?
Hi, Dean. It's been a while. I was curious what like the using side channels for these manifests is obviously one approach. Like another approach would be to like store these manifests in various ways in the encoded data itself. Do you have any thoughts on that? Like indexes of subgraphs, for example, like stored throughout the DAG, that kind of thing.
Yeah. So the short version is that these are two different problems, right? So the thing that you're handed, right? The thing the user needs to do is that they have some description of the data and they need to be able to get it and verify that it's correct. So if the thing I have is coming from Docker Hub is a SHA-256 of 100 megabyte object, I cannot add data to that object without changing the hash. So I'm out of luck. However, and I think this goes to like some stuff that Juan mentioned in the last talk. And part of why I think it's important to lean on some of like the IPLD tooling and have support and things like for IPLD URIs and gateways is there are better formats than UnixFS for representing data. Like I swear, it's true. And so when, I hear things like, Rudiger mentioned, oh, I would, or Friedel mentioned, hey, I would love if we could just have the links really separate from the data and all be sort of traversable this way with like minimal parsing. I say that sounds pretty cool. We need to make sure you can do those things and have them work and like, other tooling people want to use, like, gateways and other sorts of resolvers, right? So that you can build the data structures, like putting a manifest inside the data structure and then referencing the root as like manifest over here, data over here. That sounds fine. But you have to, that's a new data structure. So you both have to get people to use it and then make sure it's actually usable by them.
Yeah, definitely. It'd be a trade-off between like, you'd have to pre-compute the data structure, right? And know upfront what the access pattern would be.
Yeah, and you might know.
But then you don't need
right?
a side channel.
Right, you might know. So you might say, I forget the details of how BitTorrent v2 does this, but they basically, I don't think the info hash contains all effectively like the block data anymore. That's like deeper in the graph, but you can still fetch the manifests and get all the blocks without having to do like binary tree walking down to 16 kilobyte chunks, which would be sad, right? Like they know how their stuff's going to be accessed. It's like, okay, that's cool. All right, you allow for optimizations when you know your stuff.
So do we need a better data encoding?
Yeah. So I think there's like two pieces of this. And I'm just going to throw in like one sort of side channel pot shot while I'm here. What we use to like the data protocol is, we don't really care. We haven't talked about transports really. I've seen like people do TCP or Quick or whatever. you want to make these things HTTP, that's also totally cool. Like making an HTTP version of Bitswap would take like, I don't know, an hour, 2 hours. You just take the protobuf and then you send the protobuf over. Or you say, oh no, okay, then you can bike shed with people if you'd rather use JSON instead of a protobuf or whatever. But like the key question is some of these trade-offs that we're thinking about, right? Kraken Sync 1 is like an interesting trade-off. I ask more people to do compute and storage and lookups to disk in exchange for me needing less upload bandwidth when I ask for my requests. There are times that might be a really good trade-off. There's times that might be a really bad trade-off. So I think, yeah, we need the data transfer protocols. I think we need some like base scaffolding ones that give us our biggest bang for the buck. And then we're going to need some ones, and then we're going to probably need to make some data, like data structures that are better optimized for some of this, right? So if people want to make data transfer protocols that are, they don't want the user requests. They're like really bad if your user request requires any type of multi-block data structure traversal. They don't want no hamps for me. I just want to walk through blocks only. Okay, that's cool. We can make a protocol that does blocks only, but then you're going to need to make your data structures useful to people and also not require those. Right. It's like, I think those things are allowed to go hand in hand.
Yep, I agree. I'm kind of interested in this encoding space because I think it's like low hanging fruit and it's pretty relatively simple to implement. You do lose backwards compatibility with all the existing data that's out there.
And so the trick with, yeah, so one of the ways in which it's easier and harder, right, is easier because you just make a new thing and then you launch it, but it's harder because you got to get people to like use it, right? Data transfer is in many ways easier because it just lives in the background, right? You can just run a separate process, a separate thing next to it. But now what you start getting into is like, we don't really have implementations out there that are successful at using multiple data transfer protocols in parallel. But we totally should. Yeah, yet, right? So this is, I think Hugo's going to want to talk about this in a couple of weeks.
Step one is enable multiple transfer protocols. Yeah.
Right. So we can design them and then we can start playing around with them, right? Like, again, I think it would be the protocols not equal the implementation, right? I made a comment about in Guy's presentation, which is like, I just wanted to replace the words bitswap with go bitswap and like IPFS with Kubo, because like the fact that bitswap has support for say want have is, I think, not a bad thing. Like it got added because it was useful because there was too much duplicate data coming in. But you could just decide to turn off set like broadcasts, which is I have no idea who has the stuff. Hey, universe, do you have anything? Like you could just turn that part off in your implementation, right? And still have the other part of the want have.
You can't meaningfully because you get kicked off the network. Right.
No,
like
we saw
you're
this
talking
about on the server. You're talking about on the server side. I'm saying on the client
either
side.
way. If you claim to speak bitswap and you don't do the dance properly, you get added to the naughty list.
As a client, I get to choose what I'm doing. So as a client, I could decide.
You don't get to not receive messages, which is one of the.
Oh, sure. Oh, the fact that it's only one protocol instead of two protocols when it should really be like bitswap client and bitswap server. Yeah, sure. That's dumb. You just have to drop the messages, and you can do that. Like the Go client now will let you just drop those messages. So that's like, that's a protocol failure, right? That's a fixable protocol failure. That has nothing to do with blocks. It has to do with like bitswap being this wonky thing, which shoved two different protocols into the same name for some reason, right? But I do think like one of the things I saw Friedel point out and some other folks is this, like IRO cannot, for example, fix the problem with getting too many requests for want haves for garbage they want nothing to do with. They can't fix that problem.
Which
And that's
Key's work really pointed to well, right? Like the challenge we have here is one of scaling, where
but it's
1,200
not
messages is a lot.
but it's not scaling like that. That's the problem. The problem is basically spam, right? So no matter what protocol you implemented, you would still have, like, the spam that was there even before the want have messages existed.
Mhm.
People were just getting duplicate blocks back instead. So like all the spam was still there. The problem is, none of our protocols, this is a little bit like the libp2p stuff, where like, oh, hey, we need resource management, right? Like we need 429 errors. We need, you have asked me for too much stuff. Please go away. And
Also-
the fact that there's a big client on the network, which is Kubo, which is behaving terribly by spamming everyone. If we need to bump the protocol version and then say, oh, if you're on, version, X+1, we'll treat you nicely, and version X or lower, you're going to get less. I'm going to just answer your streams less because I know you're bad at stuff. Like, we can do that.
Okay, we have Hannah, then Jeropo, and then I think we will call that a day. Hannah, what's going on?
I just wanted to share that like the history of why does BitSwap broadcast requests to everyone, right? Like in the chat, Adine pointed out that I think pointed out there was like, now it broadcasts a want have to everyone. Before it broadcasts a request for a block and got back like tons of duplicate blocks. But the reason it does all of that is that originally at the time, the DHT was super duper slow. And the thought was, we simply cannot wait for the DHT to respond in order to go fetch our first, to like make a more targeted request. And so now that entire design is based around a deficiency in that may or may not exist. I think it probably still does exist to some extent, but it's just an interesting bit of information that all this, crazy. Also, I'm not sure I realized that back when I was working at GoBitswap, you weren't connected to 700 peers. You were connected to 30. That's an interesting.
It's been 600, 900 for, I think, forever.
Oh,
Forever.
really? Okay,
It's
all right,
always
never
been-
mind. Never mind.
It's always been kill your router
20, even
amounts of connections.
2018? No,
Yeah.
I don't know. All right, never mind. I don't know what I'm talking about.
Well, IPFS
Maybe I
desktop,
didn't.
Light will fix this. Light will fix this in IPFS desktop long before the Kubo defaults changed.
Yes, Jeropo.
Adin was saying that we cannot fix the spam from other node. And it's true that right now the main implementation is quite spammy, and you cannot, if you want to talk to them, you cannot fix that. However, in the future, what I think we could do, if someone just get annoyed that, oh, I'm spending too much resources answering requests that I don't care about, one thing you could do is you could have some budget logic where when someone spam you too much, you just stop responding. And if they continue spamming too much, you kill the connection. And if they open new connection, you don't open it, which is quite cheap. It's what failed to ban does, for example. That won't help those peers. So those peers will not work anymore, but they will have the choice to upgrade. And it's basically, if you have a client so bad that the only solution that people have is to not talk to you, it's a pretty good incentive for people to upgrade their client. So it's like forcing people to upgrade to a protocol that's more nice to people. But I think it's a valid strategy that we'll see at some point. If people get annoyed, then they will be forced to upgrade.
Fantastic. Who has the last word? Anyone? Hannah, did you re-raise your hand? No. Okay, cool. Well, then I think we'll call it there because we're 3 minutes over time, despite starting 5 minutes late. But thank you very much, everyone, for let's continue this conversation in the Move the Bytes working group channel on the Filecoin Slack. I have proposed a new purpose for this working group. I'm just going to run with it unless someone tells us otherwise, but I'd love to continue that discussion and refine it in chat. I think we still have lots of good stuff coming along. And thank you, as evidenced by Guy and Nadine's presentations. So join us in 2 weeks for Hannah, who is going to be presenting. Hannah, are you presenting a new protocol conception?
I mean, yeah, sort of.
It's going to be great. It's going to be great. Cool.
Yeah.
Awesome.
Stargate is the name.
Amazing. Well, thank you so much, everybody. Much appreciated, and looking forward to seeing you in 2 weeks. Thanks.